First of all, you have to learn the name of the method. This method is called, so it's a method to or for solving x prime equals ax. And it's a method for finding a particular solution. Of course, to actually solve it, then you have to add the complementary function. So we're looking for a particular solution to this system. Now, the whole cleverness of the method, which I think was discovered a couple hundred years ago by, I think, Legendre, I'm not sure. The method is called variation of parameters. I'm giving you that so that when you forget it, you'll be able to look it up at the index to some advanced engineering mathematics book or something, whatever's on your shelf. But of course, you won't remember the name either, so, so maybe this won't work. Variation of parameters. I'll explain to you why it's called that. All the cleverness is in the very first line. If you could remember the very first line, then I trust you to do the rest yourself. I don't know any motivation for this first step. But mathematics is supposed to be mysterious anyway. It keeps me eating. So xp, it says, look for a solution, and there will be one of the following form. Now, it will look exactly like, look carefully because it's going to be gone in a moment. It will look there. It will look exactly like this. But of course, it can't be this because this solves the homogeneous system. If I plug this in with these as constants, it cannot possibly be a particular solution to this because it will stop there and satisfy that with r equals 0. So the whole trick is you think of these as parameters which are now variable, as constants which are varying. That's why it's called variation of parameters. And you think of these, in other words, as functions of t. So we're going to look for a solution which has the form, since they're functions of t, I don't want to call them C1 and C2 anymore. I'll call them V because that's what most people call them. V or U sometimes. The method says, look for a solution of that form. Why should there be a solution of that form? I wish I could tell you, but I can't. I haven't met anybody else who is able to either. It just works. So the variation of parameters, these are the parameters that are now varying instead of being constants. Now, if you take it in that form and start trying to substitute it into the equation, you're going to get a mess, and you won't be able. So I think I was wrong in saying I could trust you from this point on. I can only trust you. I'll take the first step from you, and then I can trust you to do the rest after that first step. Okay, the first step is to change the way this looks. Change the way it looks by using the fundamental matrix. Remember what the fundamental matrix was? Its entries were the two columns of solutions. Okay, so these are solutions to the homogeneous equation, the homogeneous system, and I'm going to write it using the fundamental matrix as, now think about it. The fundamental matrix has its columns x1 and x2. Your instinct might be using matrix multiplication to put the V1 and the V2 here, but that won't work. You have to put them here. This says the same thing as that. Let's just take a second out to calculate. So look, the x is going to look like x. I have no notation for this. Oh, yes, I do. So x1, y1, that's my first solution. My second solution, so here's the fundamental matrix, is x2, y2. And I'm multiplying this on the right by v1, v2. Doesn't it come out right? Look, what's the thing? The top is x1 v1 plus x2 v2. The top x1 v1 plus x2 v2. It's in the wrong order, but multiplication is commutative, fortunately. And the same way, the bottom thing will be v1 y1 plus v2 y2. v1 y1 plus v2 y2. If I had written it on the other side instead, which is tempting because the v's occur on the left here, that won't work because what will I get? I'll get v1 x1 plus v2 y1, which is not at all what I want. You must put it on the right. But this is a very important thing. This is going to plague us on Monday, too. It must be written on the right and not on the left as a column vector. Okay? So the rest of the program is very simple. Substitute, I'll write it out as a program, substitute into the system, into that, in other words, and see what v has to be. That's what we're looking for. We know what the x1 and the x2 are. It's the question of what those coefficients are, and see what v is. Let's do it. I think. Okay, let's substitute. Let's see. So the system is x prime equals ax plus r. So I want to put in xp, this proposed particular solution. That's a fundamental matrix, and the v is unknown. Okay, how do I differentiate the product of two matrices? This is possibly something you did not learn in 1802 or 1802A. I know you didn't learn in 1802A because I never told those of you in 1802A. I forgot that I would need it now. And it's too much trouble to stop and derive it. But look, you differentiate the product of two matrices using the product rule that you learned the first day of 1801. Trust me. Let's do it. So I'm going to substitute in. So in other words, here's my xp, and I'm going to write in what that is. So the left-hand side is the derivative of x prime times v plus x times the derivative of v. Notice that one of these is a column vector and the other is a square matrix. That's perfectly okay. Any two matrices which are the right shape so you can multiply them together, if you want to differentiate their product, in other words, if the entries are functions of t, it's the product rule. The derivative of this times this plus that times the derivative of this. You've got to keep them in the right order. You're not allowed to shuffle them around carelessly. Okay, so that's that. What's it equal to? Well, the right-hand side is a, and now I substitute just xp in, so that's x times v plus r. So is this progress? So what's v? Looks like a mess. But it's not. Why not? It's because this is not any old matrix X. This is a matrix whose columns are solutions to the system. And what does that do? That means x prime, it satisfies that matrix differential equation. X prime is the same as ax. X prime is the same as ax. And by a little miracle, the v is tagging along in both cases. So this cancels that. And now there is very little left. The conclusion, therefore, is that xv is equal to r. Okay, what's v? It's v that we're looking for, right? It's equal to. Okay, you have to solve a matrix equation now. This is a square matrix, so you have to do it by inverting the matrix, right? You don't just sloppily divide. You multiply on which side by what matrix? Choice of left or right. You multiply by the inverse matrix, on the left or on the right? Has to be on the left. Multiply both sides by x. Oh, I see, multiply on the right. Yeah, okay. Ambiguous ambiguous. Okay, multiply both sides of the equation by x inverse on the left, and then you'll get v is equal to x inverse r. Hey, how do I know that x inverse exists? Does x inverse exist? For a matrix inverse to exist, the matrix's determinant must be not 0. Why is this determinant of this not 0? Because its columns are independent solutions. Of course, this is not right. I forgot the prime here. Okay. I'm not failing this course after all. V prime equals that, so. This is done by differentiating each entry in the column vector, and therefore we should integrate it. So it'll be the integral, just the ordinary antiderivative of x inverse times r, and this is a column vector. The entries are functions of t. You simply integrate each of those functions in turn. So integrate each entry. There's my v. And sorry, you can't tell the v's from the r's here. And so finally, the solution, the particular solution is xp. xp is equal to, it's really not bad at all. It's equal to x times v. It's equal to x times the integral of x inverse r dt. Now, actually, there isn't much work to doing that. Once you've got solved the homogeneous system and gotten the fundamental matrix, taking the inverse of a 2 by 2 matrix is almost trivial. You know, you flip those two, and you change the signs of these two, and you divide by the determinant, and multiply it by r. And the hard part is if you can do the integration. If not, you just leave it the integral sign, the way you've learned to do in this silly course, and you've still got the answer. So what about the arbitrary constant of integration? The answer is you don't need to put it in. Just find one particular solution is good enough. You don't have to put in the arbitrary constants of integration because they are already in the complementary function here. And therefore, you don't have to add them.